So with those two formulas for gravitational field strength, one of them is using information that's not to do with the source. It's using information about putting an object in the field and making an observation. And that's the first formula. So what's important here in the first formula is that mass is the mass put in the field. It's not the mass that creates the field. And the force here is the influence on that test mass. But again, we've talked about this over and over again. Since a gravitational field exists, whether we put a test mass in it or not, there ought to be a way to calculate gravitational field strength without referring to a test mass. And that method is the second formula. Take the universal gravitational constant. I put capital M here. I very often put capital M in that formula because it's the source. It's the important mass for the field over r squared. Remember the distance, little typo there, that's the distance from the center of the mass of the source. So you sometimes have to take the radius of the Earth or the radius of a planet and add an altitude above the surface to get the true value of r. Take a look at your work, please. Does anybody have any questions you would like me to go over in this section? Go ahead, Aoki. 4? So we have some unknown planet. We're given the mass. It is 4.83 times 10 to the 24 kilograms. And an object has a particular weight of 50 newtons on the planet, and the mass is 30 kilograms. What's the radius of the planet? This is an interesting question because we can answer it without using the idea of gravitational fields. But I'm going to do it using gravitational fields first. The idea is that in terms of gravitational field strength is this. And if we take this approach, because we've learned about gravitational fields, so we're going to use that formula in this lesson, I can't find the radius because I don't know the value of little g on the planet. But I also know that this formula is also a way to write gravitational field strength. But in the second formula I've written, m is the test mass. Well, this entire sentence, or this entire phrase, is talking about the test object put in the gravitational field of this planet. And the location happens to be on the surface of the planet. And what that means is we can take 50 newtons and divide by 30 kilograms and get the local value of the gravitational field strength on the surface of the planet. And you get 1.6 repeating, I believe. So the value of g is 1.6 repeating newtons per kilogram. Since I'm going to use that number in a subsequent step, in the next step, I want to carry all those decimals. Now what I can do is I can put that in here. You know, capital G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. We also have the mass of the planet is 4.83 times 10 to the 24 kilograms. This is over r squared. You know, again, this is a perfect illustration. This goes back to the first week, maybe. This is a perfect illustration why putting the units in, although it's correct and needs to be done when you show your work, makes things confusing, right? Visually, this is an assault on our senses. So if I were to say to you, if you're having difficulty rearranging that, my advice to you would be rewrite it without the units. And I say that I say that, Aoki, because if it were a written response question, you do need to show the units. So then my advice is simply, if you show the units and you're looking at it going, oh, what do I do? Rewrite it again or do it on scrap paper. Try to remember something, and we're almost halfway through the course. By the time you get to the end of the course, you're going to have written response questions on your final exam. And remember that when you show your work, all I need to see is that top formula, this line with the units, and then your answer. So anything else you do can be done on scrap paper. Okay. Anyway, looking at this, I hope you see that when you cross multiply, you get 1.6 repeating r squared equals my g times the mass of the planet, which I'm just being too lazy to write down again. So that means that r squared will be equal to g times the mass of the planet over the 1.6 repeating, and then we can take the square root. Okay, so let's try that. Now when I say g times the mass of the planet, I mean capital G. So 6.67 multiplied by 10 to the negative 11, and then I have to multiply that by the mass of the planet. Did I write that down correctly? 4.83 times 10 to the 24? Okay. And then I have to divide by the 1.6 repeating, and then I need to take the square root. So I'm getting r equals 1.39 times 10 to the 7 meters, which is the answer. My superscript on the 7 is not there, but it's correct. I did mention that there was another way you could have done this, and looking up here, this is essentially all of the work. It's a fair amount of work. What we could have done instead is said to ourselves that this weight, yes, that is the influence on the test mass, but that is also, simply speaking, the force due to gravity between the mass of the object and the mass of the planet. So we could have just put everything into Newton's universal law of gravitation. And again, the reason why that works is if you rearrange this equation for Fg over test mass, you get this statement. And that's what we did, right? We used this to calculate G, and we put the number here, and then we solve for R. Good. Good morning. Other questions? Go ahead. Number 7? So we have two planets that have the same mass. However, the gravitational field strength on one of the planets is 1.2 times the gravitational field strength on the other planet. This is a very difficult question, but I'm giving it to you to exercise those mental muscles for Physics 30. This is a classic kind of question you'd see in Physics 30. It wouldn't be gravitational field strength. It might be something like two sets of parallel plates have the same voltage, but the electric field strength in one is 1.2 times the electric field strength of the other, and then ask you to compare something. And I'm going to give you a foolproof way of solving these types of problems. Whether you're talking about planet A or planet B, everybody, this is the formula you would use to find gravitational field strength. So we have planet A and planet B, and we have this formula. I want everybody, and some of you will get to a conclusive answer very quickly here, others will need more time. I want you to look in this formula and identify any of the variables or letters in that formula that do not change when you go from planet A to planet B. So what stays the same when you go from planet A to planet B? M and big G. Okay. So these are constant. Both of these together are constant. Now we're going to play a little trick here. I'm going to cross multiply or rearrange this for those constants. So I'm going to write this as g times the mass of the planet equals little g times r squared. And remember, this is constant. I'm going to ask you what maybe you think is a silly question. Nate, why is m constant? Right. It tells you the masses are the same. Why is capital G constant? Right, that's the universal gravitational constant. So if I said to you, why is G times m constant, the answer to that question is because they both stay the same. But this is constant. And I want you to try to think about why little g times r squared is constant. Anybody have an idea why little g times r squared is constant? And the answer is not in the question. The answer is on the board. Alex? That's right. If little g r squared is equal to g times m, big G times m, and you're saying big G times m is constant, and big G times m happens to be constant because they both stay the same. But if G times m is equal to G times r squared, then G times r squared must be constant as well. Except the right side of this equation is constant because every piece of it is constant. The left side is constant because they both change in a way to keep the product constant. So if little g on the left goes up, little r has to go down to balance things out. And by following that logic, what you end up saying is that little g times r squared for planet A has to be equal to little g times r squared for planet B. Now, would you ever be given this on an exam? No, but I'm not here to teach to the exam. I'm here to prepare you for Physics 30 as well. And along the way, in doing a problem like this, as I said, you exercise your brain a little bit more. You become a more logical thinker. I'm not saying we should all be Spock and think purely logically. Emotions enter into your life, but logic is an important part of science and math. So what are we asked to find here? Well, I'm going to add a whole bunch of subscripts. I'm just distributing those subscripts on everything. What are we asked to find? Let's see. We are asked to find how does the radius of planet A compare to the radius of planet B. So let's have a discussion about comparing things in math and science. Let's say that you are 17 years old. And many of you probably are. And let's say that I am 51 years old. And I'm not. If I asked you to compare my age to your age, doing this is not a valid comparison. It is a comparison to say I am 34 years older than you. But an age difference of 34 years can mean a lot of things. It could mean, you have a child of 1 and somebody who's 35. Or you could have somebody that's 100 and somebody that's 66. The better comparison is always to divide. So when I compare my age to your age, I take my age divided by your age, and I get 3, which means my age is 3 times as big as your age. If you were asked, how does the radius of planet A compare to the radius of planet B, that's what you were asked to find. It's always a quotient, a division. And we can find that. Because if I divide both sides by the radius of B squared, I will get this. And if I divide both sides by g of a, I get that. And I hope you see that to go from RA squared over RB squared to just RA over RB, I'm going to have to take the square root of this. There is another way to do this, but it's not a really valid way. It's going to work all the time, and I'll show you it in a second, but it's not a valid way to do it. Okay? Let's try this now. What does it tell you? The gravitational field strength on A is 1.2 times the gravitational field strength on B. So what we can do here is this. For the gravitational field strength on A, I'm just going to put 1.2 times the gravitational field strength of B. It's an incredibly difficult question. These cancel, and you're left with the following for our answer. The square root of 1 over 1.2. How many of you are taking Math 20-1 next semester? So you still haven't built up those math muscles in your head yet. But you will. You know, every time you do some more math or some more physics, you're going to get more and more prepared for grade 12. And that should give you the 0.93. Approximately. 0.913, whatever it is. Yeah. I want to just address another way to do this. And the other way to do it is a really sneaky kind of way to cheat the system. You do the following. Let's make up gravitational field strengths. Okay? So I'm going to say that the gravitational field strength on B is 10 newtons per kilogram. And if the gravitational field strength on A is 1.2 times as great, it's not that big of a stretch to figure out that 1.2 times 10 is 12. Okay? And now what you can do is use this formula and this formula to find the radius. Now we also have to make up something else, don't we? The mass. But the masses are the same. So make up a mass. No matter how ridiculous the mass is, it's going to work. I'll leave it to you to figure out the why in terms of ratios and constants it's going to work. But you could use 2 kilograms for mass. It doesn't matter. What you can now do is calculate the radius of planet A and the radius of planet B and then divide them, and guaranteed you'll get the exact same answer we got. Okay. Other questions? All right, we have one lesson to cover that remains in the unit, and that is 20.2.11, true and apparent weight. And we use the word true weight. I don't really like that word. It's what we use in physics. And the reason why I don't like it is when you say, well, an object's true weight is some value, you seem to imply that the object has always got that weight, and the weight can change, right? So just to begin with, what I mean by an object's true weight is the weight when you're standing on the surface of the planet. That's the true weight. Okay? But there's this thing called apparent weight, and we're going to have to talk about the difference between the two, and then we're also going to be doing calculations with it. When your body is subjected to any kind of vertical acceleration, you feel a different weight. I'm assuming we've all been in an elevator. When you're in an elevator on a top floor and it suddenly starts to move downwards, it has to go from having a velocity of nothing, because you're at rest. I'm assuming you're getting on the elevator when it's not moving. You're not doing some kind of Bruce Willis Die Hard thing. You get on the elevator when it's not moving, you have 0 for a velocity, and then later on you're moving downward, which means you accelerate downwards at some point. You don't accelerate downward the whole time, but your downward acceleration might initially be -3 meters per second squared. And I hope you all know this feeling, and maybe I'll get the key to the elevator and we can do a little field trip tomorrow. But when it first starts moving down, you feel a little bit lighter. You don't feel weightless. You still feel as though gravity is pulling you down, but it's not as much. And I hope you would understand that if the cable in an elevator, God forbid, ever broke, you would feel weightless as you were falling, because the elevator would be accelerating down at 9.81. You would be accelerating down at 9.81. Okay? You could do an experiment. Don't actually do this because you could hurt yourself. But, you know, when you stand on a bathroom scale, it's measuring weight, right? I know it probably says kilograms or pounds, but we could scratch those out and put newtons. Well, imagine taking a pair of shoes, gluing them to the scale, stepping into the shoes, and hopping up onto a chair or a desk or something, and then jumping off. Don't do this. You'll hurt yourself because your legs are kind of glued together. But as you're falling, that scale's going to read nothing. So when you're in what we call free fall, you are weightless. That's your apparent weight. On the other hand, if you're in an elevator and suddenly it starts moving up, you feel more massive or more weight, don't you? Scratch the massive thing. I should not have said that. Your weight feels like it's more. So that's because of a vertical acceleration. The force due to gravity that acts on you stays the same. That's called your true weight. So whatever m times 9.81 is, that's your true weight. But nevertheless, you feel heavier or lighter depending on the type of motion. And this illusionary weight, this illusion that you are lighter or heavier, is what we call apparent weight. So, describe how an elevator would be moving in order for your apparent weight to increase, to be larger, to decrease, to be smaller, or to be normal. Well, if your apparent weight is more, the acceleration is up. And that direction is important. I'm going to make a very quick, minor attempt to explain why this is, and then we'll get into the details of it later. When I'm standing on a scale, and you could imagine a spring scale, but I think a bathroom scale makes more sense to us. Let's just imagine the bathroom scale is calibrated in newtons. The reason why it's registering a weight is because it's pushing against you. I know this is a backwards way of thinking. I know that you say, well, I'm pushing down on it. But the reason why it's registering a weight is that scale is being pushed up against me by a normal force, right? Okay. So really, my weight is a measure of how much that scale is pushing against my feet. But when I'm in the elevator, and the elevator is accelerating up, the scale is accelerating up. That means it's pushing against my feet even more. Whereas when I'm accelerating down, I don't like to use the word pressure, but it's a word that will work right now. When the elevator is accelerating down, the amount of force between my feet and the scale is lessened because there's not as much pressure. The elevator and the scale are accelerating down, so it lessens that force between myself and the scale. And what can you tell me if my weight is normal? Be very careful with how you answer this. Jay? Excellent. Because most people will say you're not moving, but you're stationary or you're moving at a constant velocity. In other words, zero acceleration. But that, again, as Jay pointed out, that could mean that I'm stationary or it could mean that I'm accelerating, that I'm moving rather, but not speeding up or slowing down. Okay? Well, why does your apparent weight change? Because and this is really the key to this lesson, the applied force on me by the scale changes. That's really it. And I'm going to come to a conclusion here right away, everybody, that the solution to this lesson is that the applied force on the elevator is the force that's being applied to the scale, which is the apparent weight. Okay? And I'll make that point in your notes in a second. In fact, let's make that point right now. The applied force equals the apparent. I'm going to actually use W. W is weight, which is a force, okay? Is the apparent weight. And we've actually done applied force problems. We're going to have to really review this, but I'm going to pull up a lesson from earlier in this unit. I want to show something to you. And we will spend lots of time reviewing this before we get to the exam, but I want to go back in time here. I don't know if you recall, but we had a lesson which was called Newton's second law of motion, or applications of Newton's second law of motion. And I have a feeling I'm opening the wrong one, but we'll find out. But it was a multi-day effort. We had ramps, we had friction, we had no friction. I've got a computer that's locked up right now. Let's see if I can. There we go. Try that again. Just as well I was opening the wrong one. So we were looking at applying Newton's second law. There's Newton's second law. And we were finding acceleration. But one of the days we had vertical motion problems. One of the days we had ramp problems. Well, I'm going to go to a question here, this one. And let's look at this. You've already done this, but let's read this together and think it through. What is the applied force required to accelerate a 250-gram rocket upward at 32.4 meters per second? So this is the acceleration. And that acceleration happens to be up. And the mass is 0.25 kilograms. Who can tell me why that's wrong? Because I know that if we didn't review when you wrote your exam on Friday, many of you will do this calculation and think you have the right answer. Jay? Right. We also have the force of gravity acting on it. This is the acceleration. When you multiply the acceleration by the mass, you don't get the applied force, you get what's called the net force. So you don't do that. Instead, oops, come on. There we go. Instead, you say, well, this is the object we're accelerating up. There must be an applied force upward, a force of gravity downward, and F net equals the applied force upward minus the force of gravity. Remember doing that? So you would have MA equals the applied force, which is what we're after, minus mg. So MA is not the applied force. You have to add mg. Right? Mathematically, that's what it means. And I really want to tie this to what we're doing now. Because in example 4, we had an elevator that was accelerating up, and this is what it looked like. Let's just soak that in. If the elevator is accelerating up, the applied force up must be more than the force of gravity, which means the net force is the applied force minus the force of gravity. If the elevator is accelerating down, then the force of gravity is greater, and that means the net force is the force of gravity minus the applied force. It's different. It's subtracted in a different way. What I'm telling you in this lesson, what I just wrote, is the applied force is the apparent weight. So when we take a look at this is the apparent weight right here. Except you wouldn't be using the mass of the elevator, you'd be using the mass of yourself. All right, so let's try this. A 100-kilogram astronaut is standing on a scale in a rocket. The acceleration of the rocket is 19.6 meters per second squared up. That astronaut is probably breaking more than a few rules for takeoff. I don't think you want to be standing up and accelerating at that rate. What is her true weight and her apparent weight? Well, the true weight is just the normal run-of-the-mill force due to gravity, which is m times g, which is 100 kilograms. You might say that's a fairly large mass for an astronaut, but that's including all of her equipment and suit and everything. Times 9.81. I hope, well, I know that many of you rely on calculators, but I hope you think about numbers before you automatically start plugging them in. 100 times the number means we move the decimal place 2 to the right. That's 981 newtons. What does a force of 981 newtons feel like? It feels like the force of gravity pulling 100 kilograms down towards the ground. Pick up 2 of those big water bottles, you are feeling 981 newtons. Actually, that's false. Pick up 4 of those, approximately, and you're feeling 981 newtons. So what's the apparent weight? Well, when you accelerate up, there is a force upward on the astronaut, and there is a force of gravity. By the way, the rocket is taking off from the surface of the Earth. It's not accelerating in space. So the force of gravity is still there. This is the applied force upward. This is the force of gravity, which we've already found is 981 newtons. And remember, the applied force is the apparent weight. So Newton's second law says the net force can be found by adding these forces, which would be the applied force minus the force due to gravity. It's interesting. The net force is the apparent weight minus the true weight. So I can put MA here equals the applied force minus mg. We've already calculated mg. It's 981. What is that going to give us? I'll just change color so you can see this better. 100 kilograms times 19.6 meters per second squared equals the apparent weight minus the 981 newtons. So you're going to have to find out what this is, 100 times 19.6, which is 1960. 1960 newtons equals the apparent weight, which is the applied force minus 981 newtons. $1960 plus 981 to move that over is 2941 newtons. So the apparent weight is 2,941 newtons. And although not part of the question, we can certainly compare that to the true weight. Remember, when you compare, you divide. So if I compare this to the true weight of 981, I can divide by 981, and I get about 3. This astronaut will be experiencing 3 Gs. They will feel 3 times heavier, which is why they probably shouldn't be standing. That's why you're seated, why astronauts are seated when the rocket accelerates upwards. We're going to talk about this extensively in the next unit when we talk about circular motion. But if the astronaut is seated and they're accelerating upwards towards their head, what happens is a lot of their blood gets left behind at their feet. And you have to train for that. Most people, if you put them in a 3G environment, will pass out immediately. Most, not everybody. And that's because the blood leaves your head. There are exercises you can use to increase your blood pressure by flexing your neck to keep the blood up there, and that's what they do when they put astronauts in high G training. If you watch, and we will in the next unit, astronauts being trained where they're experiencing 8, 10, 12 Gs, their whole body is contorted. All right, let's try one more. What is the magnitude of the astronaut's true weight and apparent weight if the rocket is in deep space? Well, if they're in deep space and there is that acceleration, quote, upwards of 19.6 meters per second squared, then this applied force is equal to the net force. Somebody explain why. Give me a second. Why is this a true statement now? Right. You're so far away from the Earth. Deep space means you're really, really far away from the Earth. I mean, if you're in orbit around the Earth, there's still a force of gravity, but this means really far away. So the force of gravity between you and the Earth is not there. Technically it's there, but it's so small that you would never be able to measure it. And what that means is that ma is the apparent weight. So that's 100 kilograms times 19.6 meters per second squared, which is 1960 newtons. This is the apparent weight. And this next part, this next bit of business is why I don't like the word true. What is their true weight in this situation? It is 0. But again, let me write that down first. That word true seems to imply there's something inherent about the person that they have a true weight. True weight changes. Okay? What the true weight of 0 means is if the acceleration were nothing, they wouldn't feel any weight. They would be weightless. And weightless in an environment that you might be familiar with is what you see when you see astronauts in orbit and they're weightless. They're kind of floating around. We'll get into the real details of that, but the reason they're floating around and weightless is because they're falling. They're in a free fall. I'm not sure if you know this, but when astronauts train for free fall, they go inside a plane. One of the planes has a nickname called the Vomit Comet. And they're strapped in their seats, and the plane goes up to a very, very high altitude where the air is just thick enough that they can still breathe. And then they turn the engines off and they go into a free fall. And the plane falls at 9.81 meters per second squared. And everything in the plane falls at that rate. So when you see them kind of floating around, they're really accelerating down very fast. But the plane and themselves are accelerating down at that rate, and they're experiencing weightlessness. That's what it feels like. If you want to experience weightlessness, go bungee jumping. In that short period of time until you reach the bungee length where it starts to stretch, you will feel weightless. That's what it feels like. When you go over a hill on a roller coaster, you feel a sense of weightlessness. Astronauts in orbit are falling, but they're falling around the Earth. I'm going to get a little off topic here, but I've opened this can of worms so we can talk about it. There's something called Newton's cannonball. Newton imagined going to the highest mountain on Earth and firing a cannonball horizontally off of that mountaintop. And we know what's going to happen. The cannonball goes poink and hits the ground. But he said, what if you fired it faster? So I fire it from someplace in Alaska, and it lands in the Pacific Ocean. And I fire it even faster. Instead of landing in the Pacific Ocean, it lands in France. And then I fire it even faster, and it lands in Newfoundland. And then it lands in Yukon. If I fire it fast enough, it falls around the planet and hits me on the back of the head. That's what an orbit is. It's a free fall in a circular motion. Anyway, any questions with B? Number 2, a 75-kilogram person has an apparent weight of 640 newtons while riding an elevator. What is the acceleration of the elevator? This is very important that you pay attention to this. We cannot decide whether the elevator is accelerating up or down to set up the equation until we find their true weight. You know how if the elevator is accelerating up, then it's the apparent weight or applied force minus the force of gravity equals the net force? This is an upward acceleration. Think about that for a second. That if the elevator or the person is accelerating up, the applied force is greater, upwards. But if the person or the elevator or whatever is accelerating down, it's this. Are you with me? I'm saying there's no way to know which of these two it is in this question unless we calculate the true weight. The true weight is mg, which is 75 kilograms times 9.81 newtons. Notice I put mg. I didn't put ma. It's mg for weight. How many of you, by the way, understand the elevator must be accelerating down? I mean, I'm just looking at this. I see 75 kilograms, and my mind says 750 newtons, approximately. But they weigh less, so it must be accelerating down. But let's get a number on this. 75 times 9.81 gives me 735.75. But so now you have to reason this out, that since they weigh less than their true weight, and I will quantify this for you with a statement, since the apparent weight is less than the true weight, the acceleration must be down. It has to be, because that's when you feel lighter. So there's a little bit of common sense that has to come into play here. Maybe you don't really have to understand that, because I suppose it just occurred to me. I hope you understand that the apparent weight and the true weight are always in opposite directions. So you're going to subtract the two numbers and set it equal to MA. And I suppose you could just blindly subtract them without thinking about which is up and which is down. But what's going on here is the applied force upwards taken away from the true weight equals MA rather. And by the way, we know all of this now. The apparent weight is 640. The true weight is 735.75. The mass is 75 kilograms. That's a pretty simple mathematical statement to unwind. So I'm going to subtract the 640. And now I'm going to divide by 75. And you get 1.3 meters per second squared. You do need to know which way that is. So if you just blindly subtracted them because you know it's going to be bigger minus smaller equals MA, you still have to know which one is up and which one is down to decide whether the acceleration is up or down. Okay, which one's bigger and which one's smaller? This is a downward acceleration. You still with me on that? Is that the final example? One more quick one. Okay. Well, what if they had an apparent weight of 900 newtons? Their true weight was 735.75 newtons. Did I remember that rightly? Okay, rightly? Did I remember that rightly? Sound like one of those old-timey guys. You should be able to look at that and understand that they are accelerating up because their apparent weight is greater. So this is an upward acceleration, which means MA, I'm going to cut past all of the F. Net force, which is MA, is the apparent weight of 900 newtons minus the true weight of 735.75 newtons. And again, this mass is 75 kilograms. So it's just a matter of subtracting those, dividing by the 75, and then saying, oh, by the way, it's an upward acceleration because your apparent weight is greater than your true weight. So I'm going to say the acceleration is 2.2 meters per second squared, and this time it is upward. That's the last question. Yes? When we first started analyzing applying Newton's second law, we did it to vertical motion. That's all this is. But you need to remember, apparent weight is always the applied force upward. Always. Whether you're accelerating up or down, there's an applied force upwards. If there isn't, you're in free fall. And I guess if there isn't an applied force upwards, then the applied force upwards is 0 and your apparent weight is 0. This is always true. It's just that we're using the mass of the person whose weight we're talking about. We're not using the mass of the elevator or anything else, or the rocket. What do we got here? 1, 2, 3, 4, 5. A few from your textbook to practice as well. Get started on those. Tomorrow we are going to enter into review mode. We'll review tomorrow, we'll review Thursday, and your exam is Friday. Okay. You have football Friday? Okay. Where are you playing? So get to work on that, please.